Good morning. We are on to the second last chapter of the semester. So we're going to cover simple linear regression, which means building models that can predict whether you're predicting a process, or you're predicting in time, you're forecasting. All of that are types of regression models. And in simple linear regression, you are building a model that can predict y. Okay, we put a hat on y because it's a predicted value based on some constant b0 plus b1 x. You're going to build a model that looks like this. Remember your equations from calculus, where the equation of a straight line was y equals mx plus c, right? And this was the gradient, right? And this was the constant. That's exactly what we're doing here. We're building a straight line where now you've got the b1 on the x, right? So this is the gradient, the slope, right? And this is the constant, or the intercept. You can call it either. Okay, so that's what this chapter is about. So we're going to look at how to fit a least squares regression, so that a line that best fits the model. We're going to talk about the assumptions of those models, what those coefficients mean. We're going to talk about the intercept, okay, and we're going to try to put some confidence intervals and prediction intervals on our value that we are predicting. Okay, we're going to test also for significance and look at some of the residuals. Okay, so first, when we're building models, we have to understand what we're doing. We're trying to build a relationship between y and x, right? We're trying to build a relationship between y and x. Now, usually, what we can do is we start with a graph, right? To look at relationships. What kind of a graph would you look at if you're looking at numerical variables, right? Two numerical variables, and you want to see a pattern between those two variables. So a graph that shows that is one that has y and x and a whole bunch of dots based on the data set, right? That's called a scatter plot. You have that option in Minitab to make a scatter plot, right? It's under graphs in Minitab. Okay, you put in the x variable and you put in the y variable, and Minitab will make a scatter plot for you. Remember again, the y variable is the independent variable, sorry, it's the dependent variable. Right? You can also call it the response variable. Okay, and then the x variable is the independent variable. Or you can also call it explanatory or predictor variable. Right? It's a predictor because you're using it to predict y. Right? So it's a predictor or explanatory variable. You use it to explain y. Right? So that's independent and y is dependent. So that's a response variable is what we talked about. That's y, and an explanatory variable what we talked about is x. Okay, you can use x to explain changes in the response variable. That's y. Also called a dependent variable. And a scatter plot shows the relationship between y and x. Okay, for example, you're looking at number of bots that were out on the internet at a certain period in time and the number of spams that went out based on those bots. And you think there is a relationship because bots are sending out lots of spams. Okay, If you look at it, this is what the data set looks like when you plot it. And each point is a particular data point. Okay, so you have bots on the x-axis, spams per day on the y-axis. Each point corresponds to a data point. And looking at that relationship, there seems to be some kind of a trend in the data set, right? You can try to fit a line through it. That's what we're going to try to do throughout this chapter. You have to also be careful about not just always trying to fit a line, right? Sometimes you have to look at the axis and see if it actually makes sense. Sodium and calorie, while there seems to be some kind of a relationship, right? It looks like it from the data set. Sodium and calorie, you know scientifically, is not related, right? Having excess sodium doesn't really increase your calories. And so you can then decide to not build a model even if you see some random correlation. Now, when we look at scatter plot, we're going to talk about three different things to describe that scatter plot. One is the form of that scatter plot, right? That form can be linear, right? It can be curved, right? Or you can have no pattern. This is a linear scatter plot in the first case. This is a curved scatter plot, nonlinear scatter plot in the second case. All right, so we're going to describe a scatter plot looking at a relationship. We're going to see if there's a linear one or a curved, are there clusters there, or is there no pattern. Then we're going to talk about a direction, right? If it is, let's say, linear, is the line increasing, right? Or is the line decreasing? So this is positive, this is negative. Okay? And then we're going to talk about the strength of that relationship. Basically, are these dots far away from the line, or are these dots very much close to the line? Okay, and we'll talk a little bit about outliers. There are a couple of points that's very much farther away from the rest of the trend. Okay, so when we're talking about linear relationship, you can see this is a negative linear relationship and this is a positive linear relationship. You can also have non-linear relationship, right? Something like this is a e to the x exponential relationship. Okay, exponential relationship. Something that looks like this, right? You have to remember back from calculus, that looks like a x squared, right? Parabola. Relationship. These are linear. This is a negative, and this is a positive linear relationship. Or you can have no relationship, right? In this case, y is pretty much constant irrespective of x. In this case, similarly, y is also pretty much constant irrespective of x. This one just has more variation, it's more random. This one, it's more concise. So you know what y is going to be no matter what happens in x. So in both cases, there is no relationship, right? Notice the difference. One has a lot more random error, but even in this case, there is no relationship. Y doesn't change based on x. So your model is not useful, right? It doesn't change based on x. So you always know the value of y. In this case, it's more random. You can't really even know the value of y, and there is no relationship with x. So we can have a positive linear relationship, we saw that, and a negative linear relationship, right? And we can talk about no relationship or a constant value, right? Both of them as no types of relationship. You can have strong positive linear relationship or a weak positive linear relationship, right? So if you try to fit this with a line, you'll see there is lots of gaps between the line and the actual data points. Okay, so with a strong relationship, when you use your model, you'll get a good prediction. With a weak relationship, when you use your model, you'll get a bad prediction. Okay, so when we look at, let's say, state per capita income and state median household income in the country, right? You can see there is a weak relationship between them, so it might not be that useful to try use this median household income to predict state per capita income. Whereas if you look at the average amount of gas consumption and the average number of heating degree days per day, right, because of temperature, it seems like there's a strong correlation between them, and so you can find out the average number of heating degree days per day and then try to predict the amount of gas consumption that is going to be. There's a strong relationship there, right? And we said we'll mention a little bit about outliers, and you know that outliers are basically a data point that significantly deviates away from the rest of the trend of the data points. Okay, so if you look at, let's say, GPA, right, grade point average, and you're looking at IQ score, well, it looks like most of them, there is some linear relationship between them, but there is always going to be some outliers, right? And these people, right, what does this mean? It means at a high IQ, you have a low GPA, so might not be as hardworking. Okay, and here you have a high GPA with a low IQ, so might be much more hardworking students. Okay, so you can always have outliers, you just need to know how to explain it. Additionally, when you're trying to fit a model, right, suppose you have this data, and at first you were colorblind, and so you didn't see those different colors here, right, and you just fit a straight line through it, and you would think there is a linear relationship. But then, if you studied the data deeply, right, you found out that these are 5 different clusters inside the data. So this is number of exotic species of bird on the y-axis and number of native species of birds on the x-axis. Turns out if you look at them under different habitats, right? There's different habitats in the environment, and if you look at them under different habitats, right, there is in fact a negative relationship between the two. These are 5 different habitats, and you plot them separately, there's going to be a negative relationship because you should look at the different habitats differently, not all together. So instead of having a positive relationship, it turns out to be a negative relationship. And you can see how the data can mislead you if you're not careful. Okay, and all this discussion that we've been having so far have been on straight lines, and that's what we're going to have to assume. Okay, we're going to have to assume that we have a linear relationship between the two variables. So what happens when you have something that looks like this or that, where it's nonlinear relationship, right? You're going to have to transform the data. So for example, let's say you had data that looked like this on the y and x scale, right? So you know this relationship can be explained by a line that looks like this, and you know that looks something like y equals to an x squared relationship, right? But you can't use anything that's not linear in our model. So you're going to have to transform the data so that it becomes linear. What is one way to do that? You can plot y versus x squared. And if you do that, that same graph that had a curved relationship will end up looking linear. It's transforming the data. So instead of using y and x as the two data variables, you're going to use y and x squared as the two data variables to fit into your model. Okay. And so we've talked about direction now, and we've talked about nonlinear and linear graphs. Now we need to talk about how to find out the strength of a relationship. So we can describe the strength of a relationship between two different variables, right, using this Pearson's correlation coefficient R. Okay. You may have seen it in Stat 2110 a little bit, but it only works when the two variables are numeric, right? Only works if the two variables are numeric or quantitative. Right? Categorical variables doesn't have a way to compute this R. It's measured by taking the difference between each data point and the mean and dividing it by the standard deviation of that x variable and doing the same for the y's. And summing all those deviations up and standardizing it and getting a number. Basically finding out, the average values and then having a way to measure this distance between each data point and the expected value across the x and y, right? And then minimizing that gap. So it tells you that how strong are they to that, how close are they to that line. Right. So in this case, when we're looking at the spams per day and the bots, right, using those values of averages and the standard deviation, you get an R value of 0.885. Right. That's a pretty good correlation coefficient. Okay. R values go between -1 and +1. Okay. So when R is positive, that means there's a positive relationship between the two variables. When R is negative, that means there's a negative relationship between the two variables. Right? So R positive means the line is that way. R negative means the line is that way. Okay. And R is unitless, doesn't have any units, has to be between two quantitative variables, between a response and an explanatory variables, and it is affected by outliers, right? Because we look at the mean and the standard deviation and outliers affects them. Now, some examples of R, if you look at this data set, there really isn't any pattern anywhere. So R is 0. You look at this data set, it's getting a little bit more together. You could probably fit a line through there somewhere, and so you can compute R, and you know it's decreasing, right? So therefore it's negative 0.3. In this case, it is increasing, and that's positive 0.5. Decreasing, getting more concise together, right? And so it's negative 0.7. This looks fairly nice on an increasing scale. Positive 0.9, right? So it's increasing, positive 0.9, and this is very much along a straight line, right? Great fit. That is a negative 0.99, or pretty much -1, right? Very strong relationship. So strength shows you how closely they're related, and the sign shows you the direction, positive and negative. Okay, but you can't use that on nonlinear relationships, right? R cannot be used on any kind of nonlinear relationship. It has to be linear. So you're going to have to transform the data to make it look linear. And then you can look at the R. Okay? So example. You have this data set, manatee deaths and the number of boats in the water in thousands, right? This is what it looks like. Which one of these values do you think represents the strength of this relationship? Spoiler alert. You can pause it and think about it if you don't want to hear the answer. Okay, so you know that there is a positive relationship between them, right? So there goes this answer, right? You know R value cannot be more than 1. It's between -1 and +1, so there goes that answer. If it was very close to the line, then you know R would be 1, but it's not exactly on the line, right? So R is not 1, so it's between these two. Now you know that 0.21 is fairly low, so the dots would be much farther apart than this case. In this case, you have the dots relatively close to the line, so it's 0.94. Okay. We'll also talk about R squared value, right? And you've seen that R squared when we talked about ANOVA, right? It's the same thing here. That R squared value is the amount of variance in Y that can be explained by the changes in X, right? Whether you write it as R squared or R squared or R squared, it's all the same. It is the amount of variations in the data that's explained by the model. Right? That's exactly what this is saying. It's the amount of variation in Y that is explained by the changes in X. It's the amount of variation in the data that is explained by your model. Your model is a model that explains Y by the changes in X, right? So that's exactly what we're saying. So you should remember this definition of what an R squared is. Right, so in this case, R value is -1, R squared is 1 or 100%. You can also write the R squared value as a percentage. Right. In this case, R is 0 and R squared is also 0 as a result. Okay. In this case, a much more realistic data, your R value in the spams and the bots relationship, R was 0.89 and R squared was about 78.3% or 0.783. Right, so let's say, for example, you get a question that says, if the GDP per capita explains 58% of the variation in net assets per capita, what is the correlation between GDP per capita and net assets? Okay, suppose that you know that GDP per capita and net assets are positively correlated, right? That means R will be positive. Okay, so increasing net assets per capita increases GDP per capita. That information you have to know. Then you know 58% of the variation is explained. So you know right away that your R squared value is 0.58. So your R value, which is the correlation, right? That's what you're trying to find out, is going to be the square root of 0.58, right? But you know square roots can be both positive and negative, right? So you get 0.76, it could be positive and negative. Well, you know that you know from before that they're positively correlated, so you can only have a positive answer there. That information you have to know from before, based on what you're comparing. So GDP per capita is positively always related to net assets. That'll help you find the R value. Okay. Now, correlation tells us how two things are related. What if I want to build a model then to use that correlation to try to predict things? Okay. Which line should I fit through all those data points that can help me predict the next point best? And so we come up to this concept of a regression line. Okay. The regression line that we use is called a least squares regression line or model, right? When you see in the text or anywhere they talk about a regression model or a model in general, They're talking about the equation of the line. The equation of the line that we started this discussion with. Y predicted is based on a constant plus b1 times x. Right? And so to get that equation of the line, we use what's called the least squares regression line, where you try to fit a line through the data set that minimizes the gap between the data point and the point on the line. Right? This is the actual data point, y. This is what you're predicting using your line, y predicted. And so you want to try to minimize this gap so that a line that you fit is closest in overall to all your points. Okay? And that distance is called a residual. We'll talk about that later. It's the error, right? It's what's you are predicting, but what's actually happening, the difference between them is the residual or the error. So we come up with then an equation of the line that helps you find a predicted value, y hat, based on any x, where b1 is the slope, b0 is the intercept, the constant, and you can find those values based on a whole bunch of computations on the data sets. Okay? You may have seen some of these before. The relationships are based on using the average values of y and the average values of x, and the standard deviations and covariances between the two variables. Okay, but luckily for you, you won't have to hand calculate all of this. You can just use Minitab to fit the regression model. Minitab can do all this computation for you. Okay. If you were to hand calculate it, you would have to find each value. You have to make squares, you have to make the multiplication of them, and then find the summation of each, and then try to find b0 and b1 using all those values from manually computing these values. Okay? As this in this example. But you can also use Minitab, and Minitab will exactly give you the equation of the line in this format where it says revenue is equal to 183.3, right? That's your B0 plus 15.6, that's your B1, right? Times the population, this is your X, right? And this is your Y hat, right? You're predicting it. The best fit line, right? That's also the same name for a regression model. Or a least squares regression model, whatever you want to call it, it's all the same. That's the equation of this line. Right? And then now you can use this line to predict what your revenue will be when X, or the population, equals 20.8. You just plug it in and you find out what your predicted value is. Right? Predicted. This is predicted revenue. Okay? And you know from before, you found out that the actual value, actual revenue, right, in your data set at 20.8, so somewhere around here, this value right here, that's the actual value, was 527.1, while you predicted 507.69. So the gap between them, that's the distance, right? That tiny gap, that's 19.41 in revenue. Okay, that's your residual. Now you can also find all the errors in the data set and look at if your model is good by comparing all the errors. Okay, and we're going to do that through looking at the sum of squares of the errors. Okay, and you've seen this kind of a setup in your ANOVA table before, and we're going to go back to that ANOVA table and reuse that here as well. And the mean squared error is going to be the estimator for our total variance in the data set. And the standard error S is going to be the square root of your MSE, right? So this the standard deviation of the data set, if that's what you're told to find, is going to be the square root of the mean squared error. You've seen that before in the ANOVA table. Right. So then it brings us to the point, once we have our equation of the line, y hat is equal to b0 plus b1 times x, right? How do I know if my line is good or not? Well, we are going to have to do a hypothesis test on it by either comparing the confidence intervals or actually performing a hypothesis test. Okay, so suppose I have a data set, right, that looks like that. Then I can fit a line through it, and that's exactly what I want. Versus I have another data set that looks like this, and the line is pretty much straight. So here I cannot use the model, right? So this is a no relationship. And this is a relationship. So I can use the top model, I cannot use the bottom model. Right? How do you think I should, what's the difference between these two things numerically? Like, how do I compare them? What is my key difference? What is the gradient of this line? B1. In this case, the gradient of that line is 0, right? And in this case, the gradient of that line is not equal to 0. Well, in this example, it is in fact strictly bigger than 0, right? It's positive, the gradient. I could also have, similarly, another relationship that was negative, right? Strictly 0. So all I really care about is when B1 is not equal to 0 versus when B1 is equal to 0. Because when B1 is equal to 0, I cannot use my model. When B1 is not equal to 0, I can use my model, even if it's positive or negative. And that brings you back to hypothesis testing, right? So remember, you can do a hypothesis testing by either computing a confidence interval, okay, or you can do it by computing a hypothesis test on it. If you were to compute a confidence interval, well, doing it on B0, which is the intercept, right, wherever that intercept is. So in this case, that's the intercept. In this case, that's the intercept, right? It doesn't give us any information. So we're never going to have to really look at the confidence interval on B0. So not important. Doesn't tell us much. Tells us if the intercept is 0 or not, right? Yeah, who cares? What we need to know is if the gradient is 0 or not, right? This is what's important. So we can compute a confidence interval using the value plus or minus t critical. You've seen this before, right? T critical. And that t critical depends on the degrees of freedom. Okay, that's important. Depends on the degrees of freedom of n minus 2. Okay. So T critical is on the n-2 distribution, n-2 degrees of freedom. It's a little bit different, so you have to be careful. It's not just n-1 here, it's n-2. Okay. Or instead of just doing a confidence interval, you can do a hypothesis testing. Right? You can write T-stat as B1, the value, divided by the standard error of B1. All right, again, Minitab will give you these values. And it's dependent on that n-2 degrees of freedom. Okay, but Minitab will actually do all these hypothesis tests for you and give you the p-values. So just by looking at the p-values, you'll be able to tell if this hypothesis of beta 1 versus beta 1 not equal to 0 is true or not. Okay, so a t-value will be given and a p-value next to that t-value will be given when you're doing Minitab to do the regression. The other thing I want to pay caution to is, notice when we're writing the hypothesis, it's in terms of beta, not b, right? B is the sample coefficient, the sample way of writing it. But the hypothesis is always in terms of the population parameter. It's just like when we wrote hypothesis with mu, right? When we wrote hypothesis with mu, that was the population mean, right? Whereas x bar was the sample mean. Similarly here, B1 is the sample gradient, or the gradient of the sample, right? And here beta 1 is the population gradient. So we write it in terms of that. We never know the actual value of that, but we write it in terms of that. So we do a hypothesis test. Beta 1 is computed, Minitab gives it to you, and you try to reject the hypothesis so that you can prove that beta 1 is not equal to 0, so you can use your model. Okay? And again, once you find the t-stat, everything's the same. You find t-critical or you look at the p-value. And Minitab gives you an output that looks like this. Okay, for example, you're trying to see if there's a relationship between stress and some parameter LOC. Minitab gives you this output, right? You've seen this before, analysis of variance table. Okay, you'll get that same table for running regression. Okay, you've seen the degrees of freedom, the SS, the MS, the F, and the p-value. Right, so again, MS is the SS divided by degrees of freedom. For simple linear regression, okay, for simple linear regression, that degrees of freedom is always going to be 1. Okay, what it represents is the number of x variables that's in your data set. Right? Here, there's only one x variable, LOC. When we go to the next chapter on multiple linear regression, you'll have multiple x variables. Then that number will be how many x variables there are in the model. Okay, so this just corresponds to number of x variables in model for regression. Okay, so for simple linear regression, there's one x only, one x and one y. It's going to be just that number 1. Now the other output to pay attention to, of course, you can see the r-squared value is pretty bad, only about 10%, right? And you'll notice the p-value, okay, the p-value of 0.002 is going to be the same as the p-value on the hypothesis test carried out on the coefficients. Okay, so notice how this is structured. So it says coefficient, right? This constant, let's clear that up a little bit. This constant is your B0, okay, and this LOC is your B1. Okay, even though that is the x variable, Minitab names that coefficient as the same as the x variable. Okay, and this value is the value for B1. Right, so that's right up here. And this value is the value for the constant B0. So that's right up here. 2.26, 2.26, 0.039, 0.039. Okay, this is the standard error computed on B0. Okay, so standard error of B0. And this is the standard error of B1. And so you can do the t-stat values and you can find the p-values. So this is that p-value on doing a hypothesis test. Okay, so this p-value is on a hypothesis test if beta 1 is equal to 0 versus beta 1 not equal to 0. Okay? The big takeaway is since there is only one x variable, p-value on B1 is equal to the p-value of the overall model. Okay, that's something you want to remember. This is the p-value of the overall model, right? P-value for the entire model if the model is significant or not. Okay, p-value for test of significance on overall model. Okay, that p-value is the same as that p-value because there's only one x variable. When that changes, it has multiple x variables, that won't be the case anymore and they'll be different. That's in the next chapter. So this chapter, this p-value and that p-value is going to be the same. There's only one x variable. Okay? Now, that standard error that we talked about is computed by finding the standard deviation of the data set and then normalizing it and doing the same thing for beta naught. But again, Minitab will compute it for you, so you won't have to compute it. That's just how much error is in computing those coefficients. Okay, and when we're fitting it to the ANOVA model, right, we're doing an ANOVA model, there's going to be errors. We talked about that, right? There's going to be some residuals. That's what we use to test our assumptions on the data set. Okay, and that assumptions is that the residuals have to be independent and they have to be normally distributed. Okay, very similar to ANOVA. Remember, going back to ANOVA, very similar. They have to be independent, they have to be normally distributed. Right? They also have to have constant variance. Remember, going back to ANOVA, those plots we made, we're going to make those same exact plots. Right? So our assumptions for regression is going to be very similar to ANOVA. Normality, independence, constant variance, or equal variance, whatever you want to call it. Okay, and there's going to be one more added on here, which is going to be the main assumption of fitting all of this, is linearity. right? And that linearity is not on the residuals, but linearity between x and y. Okay, between x and y. That's and. Got messy there. Okay, between x and y. And so doing then a hypothesis test on the coefficients turns out to be exactly the same as doing a hypothesis test on the F distribution on the ANOVA model, right? When we do the ANOVA, and you can then look at the p-value and compare it by looking at the F distribution, just like we did for ANOVA. Okay, and you've seen that table before. Again, like I said, this value is going to be 1 because it's the number of x variables in the model. These values are just the errors, the residuals. Mean values are the sum of squares divided by the degrees of freedom. The F value is the mean squared of the model divided by the mean squared of the error, and you find a p-value comparatively based on that F value. Okay, and then the standard deviation of the sampling distribution, right? The standard deviation of your samples is based on the residual. Okay, we said S is the square root of MSE, right? This value right here is your MSE, right? And this right here is your MSM, or you can call it mean squared. In ANOVA, we called it MSG, right? Mean squared between the groups. Here is just a model, right? So it's M squared M. This is always MSE, mean squared of the errors or residuals. So square root of that will give you the standard deviation. That's the best estimate for standard deviation of the data set. The other thing to pay attention to is R squared value. The R squared value can be computed using the sum of squares of the model, this value right here, SSM, divided by this value right here, SST, which is the total, right? SST. So SSM over SST gives you the R squared value. Right, so we're looking at this example of flu epidemics, right? And it looks like they're fairly closely related. The number of cases correlated with the number of deaths. Okay, it looks like they're fairly closely related over time. So we can try to then plot death versus cases and find the R value, 0.91. So that's a pretty good fit, right? And if we feed it to Minitab then tells us all this output. You can find the R squared value, right? SSM divided by SST. You can look at the p-values. They have to be the same, right? There's only one x variable. And so therefore, this model is significant, right? Significant model, i.e. I can use it, right? There's a slope because you rejected the null hypothesis on the slope being 0, and so the slope is not 0, so there is a slope, right? So there shows that by that line, there is a slope on that line, and I can then use this model right here, to predict the flu death that it's going to be based on flu cases. Pretty cool, right? You can apply it to your jobs out there. Most students come back to me and tell me that this is the most important thing that they do in their daily jobs when they go join in any kind of data position, or even when you're doing managerial stuff, you will have people that will talk to you about models and modeling. This is what you're going to be doing to try to predict either the future on your demand, right? When you're trying to sell something, future demand, future supply. You're trying to predict how your machine's working on a floor, trying to predict things into the future about anything, forecasting. All of this uses regression models. All right. Now let's talk a little bit more about the residuals that we sort of went over quickly. The main assumptions of those residuals, like we said, is a linearity, right? And we check that through a scatter plot, right? So you can just initially make a scatter plot between y and x and see if there is some sort of a linear relationship. If it's not linear, you're going to have to transform the data, right? Is there a linear relationship? That's what you check with your scatter plot. Then you check your constant variance assumption, right? And we've seen that plot before. Your residual versus fits, right? So this was your residuals on the y-axis, 0, and we said, you know, as long as it is within some uniform bandwidth, you're okay, right? You want uniform and randomly distributed residuals around 0. That's the constant variance assumption. You also want to do a normality test, right? Again, you get all these 4 plots in one go, right? Except for the scatter plot. So that takes care of it. But for normality, we look at that normal quantile plot, right? That looks something like this, where it's the z-score versus the x values or the y values. And we test for normality to see if it's normally distributed or not. What we're expecting to see is a line that goes right across the diagonal, right? So that's that normal quantile plot right here. That's what we look at. And that's the residual versus fits plot. And we look at independence, so that we look at residuals versus order, right? And to make sure that there is no significant pattern happening. There's no cyclic things. It's really like all over the place. Okay, it's very similar. Now, with any real data, your assumptions won't be, you know, always exactly true. That doesn't mean you don't do the problem. You still do the problem, but you make a note of it. Okay, mild departures won't really affect anything. It'll still be okay. Okay, so what we want to see is if there is significant changes, right? If there's big issues in your data set, then you report it. And you put a disclaimer, right? For like constant variance, if you see a pattern that funnels, right? If you see a pattern that funnels, then you might want to try to transform the data, right? If it does something like this, it funnels outwards or it funnels inwards, then there is an increasing error over the different x values, or there's a decreasing error over the different x values. You may have to transform the data. Ideally, you want this, right? Constant error variance. Uniformly and randomly distributed across 0, around it, right? So it's only when the relationship between x and y is not linear, then you could have something like this in your constant variance plot, right? And so you might have to then transform the data. Oops, excuse me. Transform the data. Okay, and we have to check our normality assumption. Again, you don't have to hand calculate each one of those values. You have a normal quantile plot, and you're looking out for that straight line that you need to have in a normal quantile plot. And you want independence between each of the data points. So ideally, for every sample that's collected, you don't want to see something that looks like this. Rather, you want to see something that is completely random. Okay, so something that, this is the plot that you get back from Minitab, right, when you're running a regression, right? And so this looks fair. This is a normal probability plot or normal quantile plot, same thing. So this looks fairly normally distributed, right? This has nothing to do with linearity, right? Not showing linearity. This shows normality. Okay. It's a normal probability plot. For linearity, you have to do a scatter plot. Okay, and this shows some sort of a constant variance. Yeah, there is some kind of pattern, so you have to be careful about that. All right, but this shows constant variance. This shows it's fairly random all over the place, right? So it shows independent. And so that's 3 out of your 4 assumptions, and you just have to do a scatter plot to check normality. Okay, so let's kind of do an example of how to build this in Minitab. Let's look at an example. Open up the housing prices example that's on Canvas. You've used it before, right? It's one of the data sets that we've used before, the housing prices, houses.mtw, and we'll work with that. If you haven't seen this data set before, right, on Canvas, I've put this up along with a short description of the housing prices case study. You can read it to see what each of these variables mean, right? So we have square feet, number of beds, number of bath, heat, if there's a heating if there's a heat I think if there's a heating unit in the apartment or not. Okay, the style of the house, right? It's also there's a couple of different categories, 0, 1, 2. Heat is if it has it or not, so 0 and 1. Garage, how many garages there are, number of bedrooms, number of bathrooms, age of the house, right? If it has a fireplace or not, what's the price of the house, school, if it's in a certain school district or not, if it's 2-story or not, or if it's 3-story or not. Okay, so we can try to predict, let's say maybe the price of the house by square feet. Okay, so price is what you are trying to predict, so that's your dependent variable. So for that we go to stat, regression, and down to the second option, regression, and go fit regression model. Okay, this option pops up. Under response, that's your dependent variable. We're trying to predict price. And your continuous predictor, right? Your continuous predictor is your explanatory variable. That's what you're using to predict price, so that's going to be a square feet. We're not going to use categorical predictors. You shouldn't either for now, okay? Or at least for even any other courses, you can convert categorical predictors to binary variables, and we'll learn that in the next chapter, okay, and use that instead. But don't use this option down here. Minitab just makes a separate model for each one of those and then gives it to you, which is cumbersome. Okay, so we're going to use just the first 2 options, first 2 inputs. So you're going to try to do that, and then we want to click on graphs, because that's where we go to check our assumptions. You want to click on 4 and 1 and click OK. Okay, and then click OK. There's all your assumptions, right? You've seen this plot before, we just went through it. Right, normality, constant variance, independence. And then you get all that output. Okay, we won't really worry about the outliers or unusual observations. That's the outliers. Okay, we won't worry too much about that. Okay, let's try to zoom in here. All right, so you'll see that Minitab gives you the ANOVA table, right? It gives you the p-value of regression. That's the p-value of the entire model. Okay, that's what you're going to take from the ANOVA table. You're not going to look at the coefficients p-value down here or the f-value, okay, and or the lack of fit or error or any of that. What you really need is the regression p-value. You have your r-squared value here, 68.5%. That's pretty good. And then you come down and you have the details about the coefficients. So this is your b0, b0, constant or intercept. That value is 12.21. So that's why you see it down here. Right, this is y predicted, price predicted, that's equal to the constant or the intercept plus b1, the slope. So that's where the slope comes from, 0.05. Okay, times by the x variable square feet. You have each of those values, you have the standard error of them, the t values, t stat, and the corresponding p values. Okay, don't worry about the VIF. Again, you notice that this p value
of square feet is exactly same as this p-value of the overall model, because there's only one x variable. So this shows that there is slope on that x variable, and as a result, your model is significant. Okay, so that's how we build a regression model in Minitab for one x variable. Okay. Now let's slightly touch upon what it means by a confidence interval on the output y. Okay, when we get a predicted value y hat, okay, we can construct a confidence interval on y hat. Okay, and the confidence interval on y hat will be on the mean value of y based on the output. Okay, so confidence interval on y hat is an interval on average y for a particular x variable. And it's computed as y bar plus or minus t critical times the standard error of the output. Okay, and I'll show you again in Minitab how to look at that. But if you were to construct a confidence interval, this is what it looks like on around the line. Okay, for each value of x, there is a interval for the average y. Okay, that's on the average. That, again, you need to know the difference between that and a prediction interval. Okay, a prediction interval is an interval. So prediction interval on y hat is an interval for any y given x. Okay, it's not on average y, it's on any y. And therefore, it's computed a little bit more differently. On the standard error is on the y, and it's much wider, right? It's saying that for every x, any y value that I get has to be within these bounds, whereas the average is going to be much narrower. Okay, so if we were to look at that data set with flu cases and deaths and compute their values, well, to answer your question, so here you have the confidence interval in the blue and red is the prediction interval. So at a 4,000 flu cases, right, let's take it right across that cross section, you know that the average weekly death count for a 4,000 flu cases is going to be between 300 right here and 380. So 300 and 380 between those two values. That's the average weekly death. And a prediction interval says instead of the average, when you're just looking at weekly death count, any weekly death count for 4,000 cases is going to be between 180 and 500. So the average is much narrower on the confidence interval and prediction interval is much wider. Okay, to compute those in Minitab, let's go back to our regression that we used. Okay, our response was price on that housing prices. Our continuous predictor was square feet. Okay. Now, when we want to look at the confidence intervals and the prediction intervals, we go to results. When we click on results, there's a drop-down option here. From simple tables, we use expanded tables. Okay, click OK and click OK. Then every output that you get, again, we won't look at the outliers here, we don't need it for now, but every output that you get will have the confidence interval built in. So on that beta 1, right, square feet right here, you also have the confidence interval on beta 1 and confidence interval on beta 0 and confidence intervals that you need if you want to look at the outliers. Okay, and suppose I want to find the prediction intervals and the confidence intervals on a particular value. Okay, you go to stat, regression, and this only works once you have actually built a regression model. So we just built one right now, right there. And so we can go back to regression, and you'll see this option that says predict. You can only click it once you've actually built a regression model. So you click on predict. Okay, you want to predict the price, and you want to enter it for an individual value of square feet. Let's say I want to put in a square feet of, I don't know, 1,400 square feet. I want to find out the price based on a 1,400 square feet. Click OK. It will tell you that the price is going to be right under here, fit, and it's going to be 81 based on this prices of 59, 64, and so on. I think these are in thousands or hundred thousands. So it's going to be 81 hundred thousands, right? And you have the confidence interval and you have the prediction interval. Notice that the prediction interval is much wider than the confidence interval. And this is what you're looking at, that comparison. This is the average price output that you expect between 77 and 84 for a square feet house of 1,500 or 1,400. Right? And that's the prediction interval. That's any price that you expect at that particular square feet. Okay, and we close this chapter with my final, again, kind of a warning or a heads up that I give. It's very easy to try build models all the time, but causation is not implied by association or correlation. Okay? So when we build models and we see relationships, that shows correlation or association. Okay, correlation is not causation. Just because there's two things that are correlated doesn't mean one is causing the other. Okay, for example, there's high positive correlation between the number of TV sets per person and the average life expectancy in world's nation. So could we lengthen the people of Rwanda by shipping them more TV? Right? That's not causation. Okay? That's just correlation. There might be underlying factors. That means that if there's more TV, there is better technology. Better technology means better healthcare and so on, and therefore life expectancy is better. Right? But one correlated to the other doesn't mean one causes the other. Okay, that brings an end to this chapter. Again, make sure you do the homeworks associated with these chapters. Okay, and keep me posted on any questions. My email address is aroy@bgsu.edu. I'll see you for the final chapter in the upcoming module section. Thank you.